the quiz is going to cover anything we did on 1-5 to 1-6. Now remember, 1-5 we broke up into 4 pieces. So, you know what I mean, there's quite a few things to look at. I would definitely look over your parent functions. Remember that parent function quiz we took? I would definitely look over the parent functions so that you have those fresh in your mind, because that's going to be an essential part of what's going to be on the quiz. Okay, so let's take a look at number 1. Number 1 says to use the graph of f of x equals the square root of x to graph g of x. Okay, so the thing that I would do, okay, let's make f of x. I'm going to make f of x in green. Remember, there were 3 points that we could make for the accuracy of a square root. If you plug in 0, you get 0. If you plug in 1, you get 1. If you plug in 4, you get 2. So remember, it's the swoop to the right. So let's graph that. Okay. So that is our original parent function, f of x in green. Okay, now let's talk about g of x. If you look at the square root part, it has a +3. Okay, so for a square root, you really set that equal to 0. Where will it start if that thing, where will it be 0? Because the square root of 0 is 0. And that's its starting place. And that would be at -3. And then it's not a bad idea to ask yourself, well, when will it equal 1? And so if you solve for x, you get -2. And then it's not a bad idea to ask yourself, when will it equal 4? Because square roots are very specific. I usually will take the inside of the square root and say, well, where is it 0, where is it 1, and where is it 4? And then we get 1. So for this one, I would plug in -3, -2, and 1. The reason I will do that is I'll get a nice perfect square. Now, you'll notice that the formula itself has that +1 at the end. That does not affect what's inside the square root. It's where the inside equals 0, the inside equals 1, and the inside equals 4. So now, if we plug in -3, we get 0. The square root of that is 0 plus 1. So 0 plus 1 is 1. If we plug in -2, -2 plus 3 is 1. The square root of 1 is 1. 1 plus 1 is 2. And then finally, if we plug in 1, we get the square root of 4, which is 2. 2 plus 1 is 3. Now, if we were to describe what's happening, the inside addition of 3, the +3 on the inside moves it to the left 3. The +1 on the outside moves it up 1. So if I just said, how is this going to change? We're going to move all these points left 3 and up 1. So if you move all the points left 3 and up 1, left 3 and up 1, left 3 and up 1, those are the points. But if you look at this, it's the same thing. -3, 1, -2, 2, 1, 3. So you are allowed for any of these functions to plug in points. Knowing what to anticipate is happening is a good idea, okay? So knowing it's going to go left 3 and up 1 is a good idea. Do we have any questions about the first problem? Did that make sense how we got that? Okay, so make sure you look over the 8 parent graphs because we'll be using them, okay? So if you add on the inside, you move left. If you subtract on the inside, you move right. If you add on the outside, you go up. If you subtract on the outside, you go down. You're good.
Wait, when does it go down?
So it goes down when you subtract on the outside. So if that plus 1 was a minus 1, the function will go down 1.
Okay.
So anything on the outside affects how it goes up or down. And the outside kind of does what you expect it to do. If you add, you think you should go up. If you subtract, you should go down. Okay? Okay. Now let's do number 2. Now our parent function this time is RV. Knowing what the parent function looks like is always a good idea. If I could draw a straight line, it would be helpful. So that's your parent function. Now, for one that has a number on our x, if there is a number bigger than 1 on our x attached to it, it will look closer to the y-axis. It'll be compressed closer to the y-axis. But I don't necessarily always remember that. So for this, I just say, since our good points are 0, 1, and negative 1, if you set 2x equal to 0, you still get 0. And as long as you plug in something exactly equal to the left and to the right of that, once you know what the center is of any square root, of any absolute value, as long as you just go 1 away above and below, or 2 away above and below, your choice. As long as you're going the same distance away, you're good to go. Okay, so we're just going to plug into the function. So we're going to substitute right here, negative 1, 0, and 1. If you plug negative 1 in, you get the negative absolute value of negative 2. The absolute value of negative 2 is positive 2, but there was a negative on the outside. That negative on the outside is not going to change, and so that's why we get negative 2. If you plug in 0, you get the negative absolute value of 0, which is 0. If you plug in 1, you get the negative absolute value of 2, which is negative 2. Now, you know you did an absolute value right if these are equidistant, then these two should always match. If these are equidistant away from your vertex, these should always match. And that's a great way to know you graphed an absolute value correctly. So now it's just a matter of putting on the points. The negative out front should flip it across the x-axis. The 2 makes it closer to the y-axis. It compresses it inward, so it kind of looks skinnier. If it was a 1/2, it actually looks wider. So that's what we should expect is happening. Okay, so at negative 1, we're at negative 2. At 0, we're at 0. At negative 1, we are also at negative 2. So our V is skinnier and upside down. Skinnier and upside down. So that's what we should expect is happening to a function where we have a negative on the outside and a 2 on the inside. So a negative in front flips it across the x-axis. A negative inside by the x flips it across the y-axis. So that are the first two. Are we good?
Mm-hmm.
Okay. Now the graph for number 3. Do you have a graph on yours? In this graph paper, do you have anything there? Huh?
Well, there's a graph there, yeah.
Can I see yours? Because I don't have a graph there. Because I'm like, what graph are they talking about?
Like that, you mean? Yeah, it just looks like yours.
Oh, okay. Then we're going to add a graph on. Bless you. Okay, so on your graph paper, could you please graph the following? Okay, so put those 5 points on for me. We're going to call this g of x. I'll give you a second to draw that. Okay, let's read the instructions. It says, describe how the graph of f of x equals x squared, gosh, I don't know why that's so fuzzy, and g of x are related, then write an equation for g of x. Okay, so let's think about the fact that our x squared function, I'm going to do in purple, looks like this. Okay, so that's our parent function. Now, is it pointed in the same direction as the original? No. So there has to be a negative out front. Okay. Has the center, the vertex, moved to the left or right at all? Has this point moved to the left or right at all? Has this point moved left or right?
Left.
From blue to purple. I'm sorry, from purple to blue.
Right.
Yes, it's gone to the right. How many units?
2.
Okay, so let's make ourselves a note. It's gone to the right 2. Okay, so we've gone to the right 2, and have we gone up or down? We've gone up 2, okay? Now, let's talk about what that means. We have to flip it. So we have to put a negative out front. To move it to the right 2, we are going to have to subtract on the inside. To go up 2, we have to add on the outside. So that's what we have to do to the original function to get our blue function, okay? So our g of x function has to be a square in order to make a parabola. We need a negative on the outside to flip it upside down. We need a subtraction of 2 on the inside to move it to the right, and an addition of 2 on the outside to move it up. Now, one of the best ways to check your work, to check your equation and your graph should always verify each other. If you plug in 2, that's my vertex, I better get 2, that's this point right here. If I plug in 2, I better get a height of 2. If I plug in 1, I better get 1. If I plug in 3, I also will get 1. So I'm just verifying that my equation does that. Well, if you plug in 1, you get negative 1 squared, which is 1. 1 minus, with a negative in front is negative 1, plus 2 is 1. So that works. If you plug in 2, you get 0 plus 2, which is 2. If you plug in 3, you get negative 1 plus 2, or 1. So these points on the graph should be verified with the equation that you've created. Make sense? How you can check your work? Okay. So that is our answer. Yeah.
What does the top thing say? Flip negative what?
Negative out front.
Okay.
Sorry. You can't read that chicken scratch number there. or letters? Okay. So that is your answer for number 3. Okay, let's look at number 4.
Wait, hold on, can you back up a
No
little bit?
problem.
Okay.
Okay. Now, for problem number 4, our f of x function has to be the absolute value because there's an absolute value there. Okay. Our g of x function, this plus 2 on the inside is going to move it to the left 2. The minus 3 on the outside is going to move it down 3. And this 2 here, anything on the outside bigger than 1, will stretch it upward. So it's going to make it higher than usual. Okay. Now, what's great is we can just, graph things. I'm going to put f of x in green. That's just our v. They are counting by 2s on this graph paper. But that's what our v looks like. 2, 2, negative 2, 2, 4, 4, negative 4, 4, 0, 0. Okay. So that's the original. Now, it's not a bad idea to, for an absolute value, to find 3 points. Where does the inside equal 0? So x plus 2 equals 0. Should verify that we've moved to the left 2, because we would have to subtract 2 from both sides to solve that. So our vertex is technically at negative 2. That's great. That's exactly what we expect to happen. Now, a vertex has symmetry, or I'm sorry, absolute value has symmetry very similar to a quadratic. So plugging in a point to the left of the center or vertex and the right is important. So here we could just plug in negative 3 and negative 1. As long as those two match, when we plug them in, we know we have found the correct vertex. So once you find the center of a quadratic, of an absolute value, and sometimes even a cubic, it's not a bad idea to plug in something one below it and one above it. We should know that this is going to happen, that it's going to be stretched higher. It's going to move left 2 and down 3. It's not flipped over, still a V, but it's a little skinnier and higher. Move left, down 3. Okay, so let's plug in the vertex first. If you plug in negative 2 right there, you get 0 on the inside of an absolute value, 0. 2 times 0, 0, and minus 3. So this is going to be 0 minus 3, or negative 3. We should expect that the center has moved down 3. Okay. Now let's plug in negative 3 and negative 1. Those should match because they're making that V. Okay. If we plug in negative 3, we get the absolute value of negative 1, which is 1. 2 times 1 is 2. Minus 3 is negative 1. We should get the same thing when we plug in negative 1 if we did it right. Negative 1 plus 2 is 1. Absolute value, that's 1. Times 2 is 2. 2 minus 3 is still negative 1. So remember, if you've chosen the correct vertex, just pick something above and below it. These two should match. And now we're ready to graph our V. Because you can plug in points, but expecting what can happen is very important. So if I plug in negative 3, which is, because remember they're counting by 2s, there's negative 3. Negative 3, negative 1 is here. Negative 2, negative 3 is here. Negative 1 is here. So they're kind of in the halfway junctures there. These are two other good points if you like seeing the whole points there. make your V. Okay. So knowing your parent, looking over the rules, hey, how do I move it left and right? How do I move it up and down? How do I flip it? How do I compress it or stretch it? If there's a compression or stretch on it, I do tend to always plug in numbers. For these ones, you can kind of somewhat guess what happened to it. But plugging in numbers is always a useful tool. You guys good with those two questions? Good? Okay. Now, in number 5, here's a piecewise function. Let's make this an absolute value. I will not have any graphs on the test that are step function unless maybe I gave you a bonus. So make those absolute value bars. Okay. So the first thing you want to do anytime you see a piecewise function, we have a border at -3, -2, 2, and 4 and 6. So there's lots of little dashed lines on here. So let's go ahead and make our dashed lines. Okay, so over at -3, put a dashed line. At -2, at +2, at 4, and at 6. So I like to always just put those on as a borderline marker, okay? So then let's look at what they told us about this first piece. So this one, I'm going to make it green. And I know that it's anything less than -3. So it lives over here. Let me scooch it down a little bit. Okay, so it's anything that's less than -3.
I can't even tell which one are the dotted line.
So there's a dotted line at -3, -2, +2, 4, and 6. So all I'm using are these numbers right here, okay? So there's a dashed line at -3, -2, +2, 4, and 6. -3, -2, +2, 4, and 6. Okay. Now you'll notice that I'm allowed to equal -3, so I'm allowed to land on the -3 border, and I am always stuck at -1. So that means that I'm allowed to land here, and that I'm always stuck at a value of -1. I don't know why it's being so stubborn. Okay, so it's just a little horizontal chunk at -1. Okay, now this piece, I'm going to make kind of like a pinkish red, lives between -2 and +2. So it lives in there. Now it's just a line. So a line can be determined by 2 points. It's going to be open here and closed here. Okay, because the open, remember, for no equal to, closed for equal to. So for a line, I just need 2 points. So let's plug in -2 and +2 into this equation. 1 plus -2 is -1. 1 plus 2 is 3. At -2, I am at -1, but it's an open circle. At 2, I'm at 3 with a closed circle. And I'm the line connecting them. And then finally, this last one, we're going to make an absolute value between 4 and 6. Now, in absolute values of v, between 4 and 6, the absolute value does nothing. So it's just at 4, I'm still at 4. At 6, I'm still at 6. The v is here and here, but I only want this little section of the v right here. It's like the other part is invisible. So I only want the v from here to here. They both have the equal to bar on them. So that's why they're closed in dots. So keep them closed in dots. And that's your graph. I mean, it's funky, but you just have to think about what each piece stands for. So this is a horizontal line, so draw that in that section. This is a regular line, so draw that in that section. This is a V, but its V is going upward on that side, so you only use that chunk of the V on that side. What I'll sometimes do is I'll sometimes make a little dashed V and then erase, or sometimes I'll just leave the dashed V and just color it in the region that it lives. It lives between 4 and 6. Does that make sense for number 5? Everybody good with number 5? Okay, let's look at number 6. Number 6, let's take the absolute value bars off. We haven't talked about that much. Okay, so pretend those aren't there. Okay. So let's say that we want to graph f of x equals x cubed. So we're going to have the standard almost a half skinny parabola going to the right, and then a little piece kind of flipped downward. That's what a cubic looks like. If you need to know, you could plug in +1, -1, and 0. That is totally okay. That will work. Okay. So what did we say earlier happens if we add 1 on the inside? Is it going to move left, right, up, or down?
Inside, move, wait. On inside, it would be right, it would be right.
Unfortunately, just set it equal to 0, because if you set it equal to 0, you'll see where it moves instantly when you solve for x. So it does the exact opposite of what we think. It's weird. They're so strange on the inside. That's why then I don't trust myself. I always go, set it equal to 0. Let's see where that middle lives. And the middle lives actually at -1. So it's actually going to go to the left. So it's weird. Inside is always ambiguous. Set the inside equal to 0. You'll find out where the center has moved. That's probably the easiest way to go. So if we just pick up each one of these points and scooch them over, that's not to the left, to the left one. If we take each one of those points and move them to the left one, we get the new graph. So we should expect that the new graph lives right here. The new graph lives right there. But you can always plug in some points. Remember, if you plug in the new center, 1 to the left of it, 1 to the right of it, you will get points that will verify your thinking, oh yeah, it moved 1 to the left. Okay. If you plug in -2, you get -1 cubed, which is -1. If you plug in -1, you get 0 cubed, which is 0. If you plug in 0, you get 1 cubed, which is 1, which is exactly what our picture in that pink color did. It moved every point, jumped 1 unit to the left. So that's what's bad about the inside. The inside does the exact opposite of what we expect. So be careful with that, because that is what happens. It moves the opposite of what we think. Okay, everybody good with this first page? Okay, function operations will be the next part. Let me see if I can get this so it's not quite so wonky. There we go. Okay. Now, for function operations, we're not going to do all of these, okay? So just whatever I do, you do. Feel free to skip if I skip. Okay. So let's just start out and let's do number 1. And let me kind of open up the quiz and let me see what type of functions I put on the quiz, just so then we're kind of consistent. Okay, so let's take a look at problem number 1. So what we're going to do with number 1 is we are going to use that function 4 times. I did not talk about the domain. I just didn't. I don't know. Okay, number 1. Okay, if we do f plus g of x, let's start there. Remember, that just means f of x plus g of x. So we're just going to write down the f of x function. We're going to write down with a plus between them the g of x function. And we're just going to combine like terms. Don't overthink it. Just write them down and add them up. There's nothing to add the square to. There's nothing to add the 5x to. The only like terms are the 8 and the negative 6. 8 minus 6 is positive 2. You're done. You list the 2 functions, you add them together. Now, if we subtract 2 functions, we do have to be a little careful. It is f of x minus g of x. And when we go to subtract them, you must put the last function in parentheses. Now, the reason you want to put it in parentheses is so that you remember to distribute in this negative to both pieces. You are subtracting the last function, so make sure that you understand that as you go through that process. Okay? And so we get 2x squared plus 8 minus 5x plus 6. See how it changed the sign of this one and this one. Distribute to both, please. Then do exactly what we did for the first. It would be 2x squared minus 5x plus 14. Let's talk about their multiplication, f times g of x. That's just f of x times g of x. My suggestion there is to start out and put both things in parentheses. So we would put 2x squared plus 8 in parentheses. We would put 5x minus 6 in parentheses. So when multiplying 2 functions, you have to put them both in parentheses. And most of the time from there, we have to use the distributive property. So let's distribute the 2x squared. We get 10x cubed minus 12x squared. Remember, when you're adding x, when you're multiplying x's, you add the exponents. And then we're going to distribute the 8 to both of those. When we distribute the 8 to both of those, we get 40x minus 48. Now, it just so happens that those ones have no like terms, So you stop there. It's just a big old list, okay? And then lastly, it was f of g, or f divided by g of x. And that's just f of x divided by g of x. And so you just write the f function on top of your fraction, write the g of x function on the bottom. Now, all of these functions' domains are all real numbers, and the same thing holds true for the answer except for this one. If you divide, 5x minus 6 is not allowed to equal 0. And that's the only value that gets thrown out, okay? And then the last one I want to do before the bell is, I just got to find it. Let's just do number 4, okay? And then you'll turn this in, okay? And this is what your quiz is going to look like. For number 4, it says to find f of g of x, g of f of x, and f of g of 3. Okay? So first, we're going to start out with f of g of 3.
Can you go back to the last more?
Oh, yeah. Let's go we're going to find 3 things. I'm going to write them up here. You good? You got it? Okay. So let's take and do f of g of 3 for those functions first. So you have to follow order of operations in a kind of bizarre way for function composition. We're going to plug 3 into our g function. We're going to put a 3 in right here. We're going to get a 9. This becomes a 9. And then we're just going to take f of 9. So don't overthink it. Please, don't overthink it. F of 9 is just 2 times 9 cubed minus 3 times 9 squared plus 1. I don't know what that is. That's 2 times 729 minus 3 times 81 plus 1. I assume from that point you'd plug it into a calculator, okay? But I want to talk about what is f of g of x and what is g of f of x. Okay, so let's try to get those 2 done as much as we can before the bell. F of g of x. Okay, so these are the f and g's we're using right here. That is the same as taking the f function and plugging in g of x. So we're going to take the f function, and wherever we see x, we're going to put in 3x. So it's 2 times 3x cubed minus 3 times 3x squared plus 1. And then we would reduce it down, okay? Now make sure when you follow order of operations, if we have time, I'll do it, but right now, let's just look at the difference. This is g of f of x. So this time, we are plugging f of x right here. So it's just 3 times that. Thank you, you too. And then I'll finish this one for you tomorrow so that you have it, okay? So,
Turn that in right now. Or do you want to?
you can wait till tomorrow. Yeah, you can wait till tomorrow. So then we would get 2 times 27x cubed minus 3 times 9x squared plus 1, which would give us 54x cubed minus 27x squared plus 1. So it's a much different procedure if you put one into the other or then switch it out. So be careful. So that would be your final answer for f of g of x. G of f of x is easier because it's just 3 times the f of x function. So it's going to be 6x cubed minus 27x squared plus 3. So if we put the f function into the g function, we get a much nicer answer. So you have to be careful as to which comes first. So it's always this function goes into the other. This function goes into the other. So just watch that as you go through that process. So then I'm going to do 3 just to make sure that you kind of get this one more time, and then that should be what your quiz is like, okay? So if you take a look at number 3, let's do f of g of x first. Now remember, that's the f function. We're going to plug in g. So we're going to take the f function and we're going to plug in x minus 3. That's our g function. And it's going to go right there. So it's really going to become x minus 3 plus 5, which is x plus 2. Now, if we take g of f of x, we're going to take the f function, the g function. We're going to plug in the f function. So we're going to take the g function, and we're going to plug x plus 5 into it. It's going to go right there. So it's going to be x plus 5 minus 3, which is x plus 2. Now, most of the time, you don't get the same answer. So that is very uncommon. I just want to show you those are linear functions, so that does come out to be nice. And so then f of g of 3, you plug 3 into the g function, you get 0. And then you plug 0 into the f function, and you get 5. Okay? So you could have also, if you did the calculation that f of g is x plus 2, and you plug in 3, you should get 5. So that's another way to do it. So that's what you're on your quiz. So that's what you want to study. I'd go over and look at any notes we've taken or any videos from 1.5 and 1.6. There you go.